And first of all, thanks to the organizers for giving me the opportunity to give this talk. This is about a joint project with David Evans, and it's about higher twisted K-theory of Lie groups. And to give you a motivation for this whole project, I need to start talking with a little explanation of the representation theory of loop groups. So what do I mean by loop groups? So it's a compact, simply connected Lie group. For the talk, you can think of SUN if you like. Then by the loop group LG, we mean like the free loops inside the group. So all of the smooth maps of S1 into your group. And this group, so I'm going to talk about a little bit about the representation theory of this group. And the representation theory will consist of projective representations. So we need some central U1 extension of this group. And you can construct that, looks like this, LG hat in the middle here. And it's constructed from this Lie algebra co-cycle, which I've just added for completeness here. You don't have to remember for the talk what this looks like. You can integrate this to a central S1 U1 extension of this loop. And then you look at representations. So what you can do is you can fix a level K and look at the so-called positive energy representations of the loop group at level K. And these are strongly continuous unitary representations of this semi-direct product here, where so the R here comes from, so the circle acts on LG by rotating the circle of the loop group. And then that lifts to an R action on this central extension. And then positive energy means that the generator of this R part here has positive spectrum. And level K means that the central circle U1 here acts by this character Z to the K. And then if you look at all of these positive energy representations of a fixed level, you can form formal differences of these. And in fact, you end up with a ring. I will say a few things about the ring structure on the next slide. And that's called the so-called Verlinde ring of positive energy representations. All right. As I said, this is a ring. It's a ring with respect to the fusion product. And you can also work out that it's a quotient of the ordinary representation ring of the group by the so-called fusion ideal. And then you can also look at the representation category underlying these positive energy representations. So that would be rep KLG. And that turns out to be a modular tensor category. And just to illustrate a little bit what happens when you go from RG to this quotient here, I've just drawn a little cartoon here for SU3. So these dots here, they mark the irreducible representations of SU3, right? So this is like the vial alcove. And then what happens if you go to, for example, SU3 at level 3 is you quotient out and end up with this finite collection of irreducibles here. Right.
G is semi-simple.
Yes, yeah. SU, yeah, I mean, this is in this particular example of SU3 anyway, yeah. Right, okay, so these groups are, of course, related to mathematical physics, which I guess is why I'm here. One thing that you can do is, for example, you can look at the vacuum representation at level K. Then you can, for every open interval of the circle, you can look at the loops that are supported in that interval, take the pre-image in the central extension, take the representation, and just form the associated von Neumann algebra. And these von Neumann algebras here, they will form the so-called loop group net at level K. And I think, I mean, this is so Wasserman has proven that if you work out the fusion for that particular conformal net, at least in the case of SUN at level K, then that is isomorphic to the Verlinde ring of SUN at level K. The conjecture is that this is true in much more generality. Yeah.
Some claim that there is proof for every.
Okay, okay. I would love to know where. So if you... Okay. The other reason why this is interesting is that this modular tensor category that came up from this positive energy representations also plays a role in Chern-Simons theory, right? So this is what Chern-Simons theory associates to the circle. So there you go. So at least two reasons why this is important for mathematical physics. And then to get to the title of my talk, so there's a connection of all of this to K-theory, right? To twisted K-theory. And that's through a theorem by Freed, Hopkins, and Telemann. So, and what they've proven is more general than what I've stated here, but just for simplicity, let's assume that G is our simply connected compact Lie group, and we have the free loop group. You have the Wallinder ring on the right-hand side of this isomorphism. And now what I'm trying to convince you of is that the left-hand side is actually something that one can compute, despite the fact that it looks like a big mess.
What is free loop group?
So you could also look at the based loop group, right? So as opposed to based loops, I'm looking at the free. Right, so what's the left-hand side? So the left-hand side is twisted equivariant K-theory of the group G. So K-theory is something that you apply to a space. The space here is the group itself, acting on itself by adjoint action, so by conjugation. And then you take the equivariant K-theory, but you do that with a twist. And don't worry, I will say a few words about K-theory on the next slide. But one thing that you can get the left-hand side here in terms of operator algebras. And one way to get this is, so from this twist here, you can construct a G equivariant bundle of compact operators over your group. And then this twisted equivariant K-theory that you have on the left-hand side is nothing but the operator algebraic K-theory of the section algebra of this bundle. And I'm going to tell you how to construct this bundle here as well. But since this is a conference in mathematical physics, I also thought that I should say a few words about what K-theory actually is. The idea of K-theory is very simple. If I have a topological space, then what I do is for K0, I look at the vector bundles over my topological space up to isomorphism. I form formal differences, and then I get an abelian group out of that. And that is something that has a straightforward generalization to C-star algebras, because what is a vector bundle really? It's a finitely generated projective module over the continuous functions. So, and then you can just generalize this to arbitrary, say, unital C-star algebras here by just taking isomorphism classes of the right kind of modules, and the right ones here are the finitely generated projective right Hilbert A modules. And then you do the same thing that you did for topological K-theory. You form sort of the group completion with respect of this monoid here with respect to the direct sum for K0. And then the next one, K1, so that's also an abelian group. That's just the path components of this infinite unitary group over your C-star algebra A. So this is the thing that you can look at the unitaries in the matrix algebra of your C-star algebra and then make the matrix algebra bigger and bigger. And that's how you end up with 0 infinity here. And in fact, so first of all, this is functorial with respect to star homomorphisms, which is nice. And then these functors extend to functors Kn of A. So these exist for all integers. K-theory is stable. Right, and I should say, so this is, I've given you the definition for unital C-star algebras, but that's just for simplicity. You can also define it for non-unital C-star algebras. It's perfectly fine. And then K-theory is stable, so it doesn't see the tensor product with the compact operators on an infinite dimensional separable Hilbert space, or in any Hilbert space. And so it's also homotopy invariant. And you have Bott periodicity, which says that there's a natural isomorphism from Ki of A to Ki plus 2 of A. So I've given you two groups, K0 and K1, and you know now everything about, or you know all the groups of K-theory essentially. All right, so that's a lightning quick overview of K-theory. So what is twisted K-theory? Well, I told you that so K-theory is stable, so it doesn't see tensoring with the compact operators. And what I mean by that is if I fix a rank 1 projection in the compact operators here, then I get a corner embedding, and that induces an isomorphism on K-theory. And so one thing that I can do is I can take topological K-theory of a space. Let's assume that this is locally compact and Hausdorff. And then I can write this as the operator algebraic K-theory of the continuous functions on my space X that vanished at infinity. That's the C0 of X. And because of this whole business, I can smuggle in the compact operators here. And so that's topological K-theory still. I haven't changed anything. And now if I want to twist this, if I want to have something that locally looks like K-theory, but somehow globally is something different, then one way of doing that would be just to replace, you can think of this as the continuous functions on X with values in the compact operators. So you can just replace that by a locally trivial bundle of compact operators, take the section algebra and take the K-theory of that. Right? So that's one way of twisting K-theory, essentially. Right? So you have this locally trivial bundle where the fibers are the compact operators, and then you do this here. And so then you can ask, so what kind of choices do I have for these bundles? And that's an old result by Dixmuir and Douady, who proved that actually these bundles are classified by the third cohomology of the underlying space. Right? So I look at the classifying space. This is a KZ3 space, and therefore I get third cohomology here.
There are bundles of any rank? Vector bundle?
Oh, no. Oh, sorry. Yeah, I forgot to say this. This is supposed to be infinite dimensional separable.
It's a bundle of infinite dimensional sections. Always. You said you have a bundle.
Yes.
But what are the fibers?
They are, so I have
Dimensional Hilbert space.
no the fibers of this is this algebra here. So it's a C-star algebra bundle where the fibers are compacts. Now I can extend this if I want to, because there's another C-star algebra that also preserves K-theory, namely this so-called infinite Kunz algebra. We have already seen the Kunz algebra O2. This is essentially the same thing, except that you now allow infinitely many generators. And it turns out that this infinite thing has the same K-theory as the complex numbers. So K-theory doesn't see the tensor product with this C-star algebra here. So I could have done the same thing, and I could have smuggled in the algebra O infinity here. And if you then use the same mantra as before, like if you want to twist that now, right? So you are allowed to change this by a locally trivial bundle where the fiber is O infinity tensor K. And you can ask again how, is there anything that classifies the twists that are of this type? And that's a result that I've proven with Marius Dadalat. So in fact, so this C-star algebra O infinity here belongs to a class of C-star algebras which are called strongly self-absorbing. And then we could show that if I look at isomorphism classes of bundles where the fiber is D tensor K, then these are actually a group with respect to the fiber-wise tensor product. And in fact, there's a cohomology theory such that the first group of this cohomology theory classifies these bundles.
For this O infinity case, do you really need K there? Is that doing work, or is that just?
Yes. So yeah, so what happens if I just take O infinity? If I just take O infinity as my fiber, then actually there are no non-trivial bundles. The automorphism group of O infinity itself is contractible. It's only if you tensor with the compact operators that you see something non-trivial. What's surprising then is that, I mean, you might then wonder, okay, so all the information comes from the compact operators. Well, that's not true, because this cohomology theory, I will explain this on the next slide, is much larger than just the third cohomology.
So these are coming from like invertible bimodules of O infinity.
Yes, yeah, right. That's a good way of thinking about this. Right, okay, so that's like higher twisted K-theory, if you want. I wanted to embed the whole story somehow into stable homotopy theory. There are some people here who know this kind of stuff, and so you can't prevent me from talking about this because I like it. So here's the idea, how to embed this into stable homotopy theory. Just think about a discrete commutative ring, so nothing fancy there. And think of the ring itself as a module over itself. And then you can ask yourself, so what are the R module automorphisms of R? And the R module automorphisms of R, if I have a commutative ring and consider it as an R module, the only thing that I can do is I can multiply by invertible element. So what I end up with is, if I look at the R module automorphisms of R, I end up with a group GL1 of R. And then I can take the classifying, this is a group, so I can take the classifying space, BGL1 of R, giving up, BGL1 of R, maybe I should just point. So BGL1 of R, and that classifies R modules of rank 1. Okay. So the thing is, I can do the same thing with a ring spectrum instead of a commutative ring, right? So a ring spectrum, in particular, one of those E-infinity ring spectra, that's like the analog of a commutative ring in stable homotopy theory. And so if I want to have the bundles of spectra that are rank 1 bundles over a ring spectrum, then I need to consider this space BGL1 of the spectrum. And so that's a thing that would classify that would be important for twisted K theory, because the idea of twisted K theory is that somehow you change, I mean, if you do ordinary K theory, you look at homotopy classes of maps from your space into the spectrum. And now for twisted K theory, you replace the homotopy classes of maps by homotopy classes of sections in a bundle of spectra. And the bundle of spectra that you want to consider should have the property that you get something that is a module over the untwisted stuff. So you end up with a rank 1 module over the untwisted theory. So this space here classifies the KUD module bundles of rank 1. And what we've shown is actually this cohomology theory that we get for these strongly self-absorbing C-star algebras is exactly of this type if you ignore this little plus here. So the plus comes from the fact that K0 is not only a group, it's an ordered group. So there's something with the order structure that doesn't play nicely here. So this is slightly smaller than the full theory. But for example, the plus will disappear once you tensor with O infinity. So that's that. Okay. Oops. So what about this bundle of compact operators? And I want to give you like one way of constructing that. And one way of getting that is to first go through something that's called a GERB over the group. And here's how you construct this GERB. You start with, so this works for G equals SUN. So you start with a groupoid over the group that you're considering over SUN. And the groupoid is very simple. It consists of triples of a group element and then 2 numbers on the unit circle without 1 that are not eigenvalues of the group element. And I've drawn what the fiber over a point, what the point GZ1, Z2 looks like in this little cartoon here. So the group element is not shown in this picture, but it is in the room with us right now. What is shown here, the red dots, these are the eigenvalues. And the way you should think about Z1 and Z2 are sort of as delimiters between these eigenvalues, right? So here you have Z1 sitting inside the circle, but between lambda 3 and lambda 4. And same with Z2. And then you can imagine that if you move the group element around, these red dots will, if you just move the group element around, these red dots will sort of dance over the circle. But if you want to stay in the same connected component of this groupoid, what can never happen is that this will jump over this. This cannot happen. So these 2 eigenvalues are sort of trapped in between the 2 delimiters here. Okay, and then I can construct from this information. Oh, I didn't tell you what the groupoid composition here is. The groupoid composition is very simple. You can compose G Z1, Z2 with G Z1, Z2, Z3, and the result will be G Z1, Z3. So you're just leaving out the middle. So it's just it's a very simple groupoid. It's a pair groupoid, if you like. And
G is the same.
Sorry?
G is the same.
G is the same, yes. Yeah, it's only composable if the G's are the same, yes. Okay. Right, then you can construct, over this groupoid, you can construct a line bundle. And here's how that works. So first of all, you pick an orientation for this circle, and the fiber over a point in this groupoid where Z1 is less than Z2 is obtained as follows. So first of all, since I have these delimiters now, I can sum up the eigenspaces in between the 2 delimiters. That works. And then I can take the top exterior power or the determinant line associated to that eigenspace. And then if I flip the orientation, so for the other part of the groupoid where Z1 is bigger than Z2, I will just take the dual, which you should think of as sort of the inverse bimodule or the inverse of this line here.
When you say eigenvalue, you're fixing a representation of the group.
Oh, I do, yes. Yeah, so I take SUN and I just use the standard representation, yes.
This is for GSU. Okay.
Yeah.
This is a line bundle over which space?
It's a line bundle over G. Right. Okay, and then this line bundle has more structure because the line bundle itself has a multiplication operation. And here's how this works. So it's easiest to describe if the 3 points, so it's sort of a multiplication that covers the groupoid multiplication here, right? So it takes the fiber over GZ1, Z2, tensored with GZ2, Z3, and produces something in GZ1, Z3. And the way this works is easiest to describe if these 3 points are ordered ascendingly, because then for this fiber here, I have this determinant line. For this fiber here, I have that determinant line. I'm taking the tensor product. But the determinant or the top exterior power has this nice property of turning direct sums into tensor products. So what I get here is that this is actually naturally isomorphic to this determinant line here. But what I'm doing here, I'm summing up all of the eigenvalues between Z1 and Z2 and the ones between Z2 and Z3. So I end up with all the eigenspaces between Z1 and Z3, which is how I have defined what this is, right? And then you only have to check that this is also compatible with this. Remember that for the opposite orientation, we use the dual line, and that somehow needs to cancel eigenspaces from this. So that's the difficult part to check. But this actually works. And then you end up with a GERB, which is a line bundle over this groupoid together with this multiplicative structure that covers the groupoid multiplication. And these GERBs have Dix-Meduadi classes as well, so the classes in third cohomology. And in fact, it was shown by Murray and Stevenson, who came up with this definition of this basic GERB, that this class is actually a generator. Right? So SUN is simply connected, so this here will just be the integers, and this here will be a generator in that group. All right. So now I've given you this GERB, which has an H3 class. I still haven't given you a bundle of compact operators. And that's what I want to do next. So, and one way of doing that I find extremely appealing because I'm an operator algebraist, is I just view this GERB as a special case of a so-called Fell bundle. So what's a Fell bundle? A saturated Fell bundle is a bundle like this over some groupoid where the fibers are Banach spaces. So this is a Banach bundle together with an associative and bilinear multiplication that covers the multiplication of the groupoid. Right? So these are this E in brackets squared. These are elements, pairs of elements from E that sit over composable elements in the groupoid. And then this is a multiplication operation, right, like this, that should be associative. And because I have a Banach bundle, I also have norms on the fibers. And I also want a star operation here that should cover the groupoid inversion. And then there are conditions, there are more conditions than I've listed here, but essentially what these conditions say is that fibers over the unit space of the groupoid should be C-star algebras with respect to these two operations here. And then if I have any fiber, this should be a Morita equivalence between the C-star algebra over the source and the C-star algebra over the target. And so that these are Morita equivalences, that's the saturated part here. So if you have a non-saturated Fell bundle, you would only have something like bimodules here and not like groupoids. So that, yeah. In the original definition, the notion of Banach bundle that they used was very, didn't have any local triviality. There was an analytic replacement for local triviality. But our Fell bundles that we will consider will all be will all come from some locally trivial stuff. That was okay. Okay, so now if I have such a fell bundle, then the nice thing is I can associate a C-star algebra to this fell bundle. And here's how this works. So if I have two compactly supported sections of this fell bundle, then because I have this multiplication in the fell bundle, one thing that I can do is I can multiply the entries of this fell bundle over composable groupoid elements. So I can just take the definition of the groupoid C-star algebra, this convolution product of the groupoid C-star algebra, and just use that instead for this fell bundle. Right? So if my fell bundle is just a trivial line bundle over the groupoid, this will just boil down to the definition of the groupoid C-star algebra. And just like with the groupoid C-star algebra, I can cook up a Hilbert module on which I can represent this convolution algebra, and then I do the usual yoga of completing it in some norm that I obtain from this Hilbert module, and then I get the reduced groupoid, reduced fell bundle C-star algebra from this. All right. So now I can do this with this line bundle with the multiplicative structure that I've considered before, right? So this I can consider this as a fell bundle where the fiber C-star algebra over the units is just very simple. It's just the complex numbers. And then from this construction, we obtain a C-star algebra. And it turns out that if I stabilize that C-star algebra, it will be isomorphic. This should be an isomorphism to section algebra of a bundle of compact operators. And then if I want a different level, so this was the generator. So if I want a different level, all I do is I tensor up this, this line bundle L, which still has a multiplicative structure. And then I take the associated locally trivial bundle of compact operators of that, take the section algebra, and then do K-theory. And the thing that I haven't talked about yet, for lack of time, is that I can do all of that in such a way that it is still equivariant. So the conjugation action of the group on itself lifts to all the structure that we've discussed. So it lifts in particular to this line bundle L. Right, so and that gives you like a description of the left-hand side of the Fried-Hawkins-Telemann theorem. Okay, and so there's one thing, right? So we have this notion of like higher twists for K-theory that is justified by stable homotopy theory. But this Fried-Hawkins-Telemann twist just is one of those twists classified by third cohomology. So you might wonder, is there anything that generalizes this, that somehow sees more of the other twists, right? Are we missing something? And so what David and I did was, this is based on the following observation. Notice that for this multiplicative structure here, the only thing that we really needed was some kind of functorial construction that turns a direct sum into a tensor product. And there's a lot more things that do that. So, so here's our input datum. So you have several categories. They are all very easy, right? So this is the category of finite dimensional complex inner product spaces and linear maps. This is the same thing, but with unitary isomorphisms. And this GR here is finite dimensional complex supervector spaces. So this is a fancy name for Z2 graded vector spaces together with a funny symmetry. So you have an odd and an even part, and if whenever you swap to odd vector spaces in your symmetry, you pick up a sign, essentially. Okay, and then we look at exponential functors on categories like the first one. So what's that? That's a functor that, first of all, should preserve unitaries. So it should be compatible with the adjoint. And then it should have this natural transformation that turns a direct sum into a tensor product. And also, if I plug in the zero vector space, I want this to be naturally isomorphic to just the complex numbers. And also, what's important is this, of course, needs to satisfy conditions. So in particular, there's a unitality condition and an associativity condition. I want that to be satisfied as well. And there are lots of examples of this. So for example, I mean, of course, the main example is if I just take this determinant line, the top exterior power, I can view this as an exponential functor. Well, it is only defined on this sub category where I have the isomorphisms, but that's good enough for our construction. And then the other functor that I can look at, or the other main example that I can look at, is the full exterior algebra itself. So just the full thing here, this is like only the top degree part, and that's the full exterior algebra. This functor here, lambda star, also has the property that it naturally transforms direct sums into tensor products. And I can also do some variation of this construction by sort of introducing coefficients if I like. So there are lots of other examples. A non-example is the symmetric algebra for a slightly stupid reason. So first of all, I want these things to be graded. Z2 graded, well, that's not a big obstacle. I can just declare my space to be trivially graded, that's fine. But I also want to end up in finite dimensional spaces, which the symmetric algebra, if I take the full symmetric algebra, doesn't do that. So I can't use that. Okay, there's a classification result as well that's based on some joint work that I had with Gandalf and Simon at Cardiff. So among the functors on vector spaces, you can classify the so-called polynomial functors by representation theory. And if you ask for a classification of the exponential functors among the polynomial functors, that's something that you can do and involves involutive R matrices. It's just that polynomial exponential functors sounds really stupid if you read this for the first time, but that's what we did. We classified those. Right. Okay, so here's the construction that I came up with together with David. So the thing is that, so the input is now one of those exponential functors. And then the output is a G equivariant saturated Fell bundle over the groupoid, and it will be the same groupoid as before. But the fiber over the units for the classical case was just the complex numbers. The fiber will now be a C star algebra, namely this C star algebra here, which is this UHF algebra. So it's an infinite tensor product of F applied to C to the N. And this is the representation, the standard representation of SUN here. So that's the same N. And then you take the infinite tensor power of that. And then you can, because this is all equivariant, you can define, you can now take the equivariant K-theory of this C star algebra. And what's also true is that if you stabilize again with the compact operators, this will turn into a locally trivial fiber bundle, locally trivial bundle of C star algebras where the fiber is D tensor. Right. So here are more details. So this groupoid is the same as before. And the only thing that changes is, well, you apply F now to the sum of these eigenspaces in between the two delimiters. And then you tensor this with this algebra D. And then you have to turn that into a bimodule or into a D-D Morita equivalence. How do you do that? Well, there is a canonical right action on the D. From the right-hand side, that's the easy one. And then you look at the left D linear transformations of this fiber. And it turns out that that is this thing here, right? So for a single eigenspace and for a sum, it will be, you will have the tensor product in here. And then it turns out that D is made in such a way that it absorbs these spaces. So there's an isomorphism like this. But it's even better than that because everything came from this exponential functor. There's a canonical choice for this isomorphism that makes everything associative and unital so that this works with the Fell bundle structure. And so what's the inverse? Well, these are now Morita equivalences. They are Morita self-equivalences of the D. So that you have an inverse, right? So you can take the opposite bimodule, and that's your inverse. And then the whole structure from before just goes through, and you get these higher twists for K-theory. And then the next question is, can you somehow compute anything of this, right? So you now have groups that you could try to compute. These ones here, right? So the equivariant K-theory groups of these Fell bundle C-star algebras. And we were able to compute this. The only drawback is that we only managed to do this after tensoring with the rational numbers, because we're using a spectral sequence, and the spectral sequence is slightly easier to handle after we rationalize. Okay, so here's the result. So if you look in the right degree, then what you end up with is, again, a quotient of a representation ring. But this time it's a slightly modified representation ring. It's this one here. So where you take the ordinary representation ring, and then you have the standard representation row. If you apply F to that, you get another representation, and you invert that, you localize that, right? So, and that's also not a surprise that this thing comes up, because if I look at this C-star algebra here and look at its K-theory, that's exactly what happens if I take K0 of this C-star algebra here. It will have the equivariant, if I take the equivariant K0 of this, the K-theory will be the representation ring localized at the end of the standard
When
representation.
it's a ring, no, it's a thing, not the K-theory group, is it just a group? You know?
The K0, yeah, usually it is, but this C-star algebra is one of those strongly absorbing ones, so you also get a ring structure, right? So,
You have a natural one.
yes.
But is the same that appear in Friedman, Hopkins, Telemann?
No, I mean, in Fried-Hopkins-Telemann, this would just have been the complex numbers, right? And
No,
then,
they also have a ring structure, no?
oh, yeah, oh, wait,
That's not the
we're
West.
talking about two different things. So this is kind of the coefficients that I'm looking at.
Ah,
And so what you are asking, is there a ring structure on this
Yes.
thing?
yes.
I will say a few words about that
Okay.
later. Okay. Right, but this is very similar to the classical case. So it's again a representation ring modulo some fusion ideal. And we were also able to identify like a nice set of generators for this ideal. I think this is what I wanted to explain next. So this is what it looks like here. Keep that in mind. So the delta here is the Vandermonde determinant. I'll explain in a second how this all goes. So to understand the generators, fix a maximal torus inside SUN. For example, you can take the one that comes from the diagonal matrices. And then what happens is that this localized representation ring is actually the same as localized representation ring of the maximal torus, but you take the Weyl group invariance in that. Right, so this is again the same as in the classical situation. So if you leave out the F, it's a classical theorem that this also holds without the F. So, but the representation ring of the maximal torus is something that is very easy to understand. It's a polynomial ring in n generators modulo the relation that if I multiply them all together, I get 1. Right, so you can also think of this as a polynomial ring in n-1 generators, which is the same thing, but I like to write it like this. Okay, and then so to give an element in here, all I need to do is I need to give you and the Sn acts on these things by permuting the variables here. So all I need to do to give you an element in here is I need to give you an element in this ring that is invariant under the permutation action, invariant polynomial. So, and one way of doing that is this formula here, right? So you have this huge determinant. This will be an anti-symmetric polynomial. And if I divide that, so so it factors out a Vandermonde determinant. And then if I take this quotient here, that will be a symmetric polynomial. That's how you get the generators. Right. So the last thing is, and maybe this also refers to your question, I mean, somehow you want to go full circle, right? So I started with loop groups. I've gone very far away from the loop group stuff. So is there any way back? Right, so, and there are a few things that I can say about that. So one thing is, if you look at the central U1 extension of the loop group, one way of obtaining that is as follows. So you can take an infinite dimensional Hilbert space, which is Z2 graded, such that the two parts themselves have infinite dimension. And on that, you can look at the so-called restricted unitary group, which are unitaries that have this form here, where the off-diagonal parts are Hilbert-Schmidt operators. And then, so this is in the book, for example, by Presley and Siegel. If I look at the identity component of this group, which is this U0 here, then there's an extension, a non-abelian extension by this group here, which is this group. So this is unitary operators on H+, such that Q minus 1 is trace class. And I didn't include the details of how this is constructed, but this is very easy. And then these operators here are nice because they have determinants. So I can just hit this with a determinant, which is the group homomorphism from this trace class unitaries operators to U1, and get a new sequence like this, right? So we have modded out the determinant. And so there is a map from LG into this group, into the restricted unitary group, into the identity component. And if you pull back this extension here to LG, you end up with exactly the Fanon extension from the beginning.
Is the level 1.
This is level 1. Yes, exactly.
So tau means that.
Tau means, oh, right, I forgot the tau here, but yeah, there's a trace, right? So these are the unitaries where Q minus 1 is trace class, and then from the determinant, you have.
Yeah, is tau. Okay.
Yeah. And so we tried this for the exterior algebra functor, but probably this is also true in much greater generality. In fact, if you have the full exterior algebra functor, it gives you a group homomorphism from this group U tau of H, not to U1, but to the unitary group of the C star algebra. Right? So in some sense, these exponential functors give you a generalization of the determinant. And then I can do the same game, play the same game as before, and end up with an extension like this. I just have to be incredibly careful what I'm doing here. This here is made in such a way that this in the middle has a group structure. A priori, this is just a principal UD bundle over this thing here. So it's not a group. But this is kind of the generalization of what you would need to, I mean, you want to generalize like the notion of level for these higher twists. So you need to end up with something that has, instead of the U1, which is the U of C that we have seen before, you need to replace that by the U of D. And that's kind of the canonical candidate. Right. So then the multiplicative structure for this thing. So this has a ring structure, right? So this is an ideal. So the question is, of course, can you somehow see this intrinsically, right? So this is sort of a ring. If I just compute it and see, oh yeah, that has a multiplication. And you kind of can. So maybe I will use the board. Because we have defined this for all SUN, right? So I can use a simple trick, right? So there are two maps on SUN times SUN with values in SU2n. The first one would just embed this diagonally, and the other one would use the multiplication and a 1. Right, and you can construct on this an homotopy between these two maps that is equivariant with respect to the conjugation action of SUN diagonally acting on here and on here. And well, if you then take this higher twist over SU2n and pull it back with respect to those two maps, then you see here that because direct sums are turned into tensor products, you get like the tensor product of the two twists. And if you do this here, you get something that, so you get the pullback of the twist with respect to the multiplication map times something that is trivial because of this. And that's kind of, and you know then that those, because you have this homotopy, you know these two bundles are isomorphic. But that's the condition that you need in the Freed-Hawkins-Telemann theorem for the multiplicativity of the twist. So that seems to repeat itself here. So, and that would give rise to an intrinsic multiplication. So you sort of see a multiplicative structure. I should say this is, yeah, there's a sketch of the proof in our paper, but take this with a grain of salt. So we didn't call this a theorem. Okay, and I think
It's an idea, and so
it's an idea, yes. I think this is everything I want to say. So here's the summary. So we've shown that the basic gerbe over SUN, so the generator of the twist from Freed-Hopkins-Telemann, can be generalized to a higher twist. We've computed the rational groups, and then we've seen that somehow the exterior algebra functor at least gives a higher version of this determinant. And then the open questions are these ones. And that's all I have to say. Thank you.